So in the last session, we discussed about environmental list, environmental variables, what are the different types of memory allocation functions, malloc, calloc, a brief introduction about memory allocation functions, and what do you mean by set jump and long jump function. Okay. So today we'll discuss about get R limit and set R limit. Okay. So every process has a set of resource limits. Okay. So every process will be allocated with certain number of resources, might be a memory or a stack. Okay. So they have their own resource limit. Okay. Some of which can be queried and can be changed. Okay. You can change or query. You can get the information about the resources using these functions. Okay. So this is a function get R limit is used for getting the information about the resources, and these are used, set is used for setting the resource limit. Okay. So each call to these two functions specifies single resources. Okay. So you cannot go for several resources, only a single resources you can specify, and the pointer for the following structure. You can see there is a pointer. Okay, so this is a pointer. So for example, if you are going for resource that is memory, then this is a pointer which will be pointing to the memory. And here you will be telling what type of memory you want. Okay, so it returns 0 if everything is okay, and non-zero on error. Then this function they make use of, you can see here, it makes use of a structure, built-in structure. This is a built-in structure with the name R limit. So here we have the structure definition. Okay, the structure R limit has got two types of limit. Okay, so here we are declaring two members of the structure. So you can see here, this one represents soft limit, that is the current limit. Okay, the current limit of the resource, and this represents hard limit, which tells the maximum value of the R limit. So maximum value, how much you can request for a particular resource. And here we have an example. Okay, so this is an example. So here, these are different types of resources. Okay, you can say R limit core, it is nothing but the core file. Okay, so if the name of the resource is core file, so you can request for the size. Okay, so a certain size of, in terms of bytes, you can request. Okay, I need around 200 bytes of core file memory. Okay, so that is represented by term. So this is the term we use. So we can use this value R limit for core, and R limit CPU. So it is nothing but you are requesting the maximum amount of CPU time in seconds. So this is one more type of resource. Okay, the process can request, I need around, for example, 20 seconds of CPU time for performing certain operations. So this is a resource. Okay. So again, if we come across, we have around 6 to 7 different types of resources. We can go through it. It is available in the notes. Okay. So similarly, memory lock. You can request for an address space in the memory. You can request for certain types of files. You can request for data segment space, heap space, uninitialized data space, okay, stack space. Okay. So here you can see not there. Okay. So here again, there is one more which we call it as R limit stack. So stack is nothing but we are requesting a certain number of bytes of data of the stack. Okay. And like that, you have different types of, here this stands for virtual memory. Okay. So this is, we are requesting certain address in virtual memory. You can see this is an example. Okay. So here we have, we are defining. So do it, it is a macro. Okay, you have studied about the macro in C. So this is a macro. Okay. So it is used for generating the string value for each resource name. So here, so do it will call the function PR limit, which is defined here. Okay, so this is the definition of function which is passing two parameters. Okay, so they are, one is the resource name, okay, and the building name you are passing. So this is the name you are going to pass. So this is a, you can see this is a character, okay, and it's of type int. Okay, and here you can see we are checking, okay, get r limit. Okay, so get r limit is used for getting information about the resource. Okay, for example, if you are passing the name as r limit cpu, okay, so name is, suppose if it is r limit cpu, then you are getting the information about the cpu time. So for particular process, how many cpu time is allocated, whether it is less than 0. So if it is less than 0, it will indicate there is error. Okay, so it will display this error message. Okay. If not, then you can get the name of the, you can display the name of the resource. Okay, and here you can display the limit. Okay, you can use this printf statement. So this will display the maximum limit of certain, that CPU, how much maximum CPU time you can request for a particular, okay, and what is the current allocated CPU time for a particular process. So this is important. Okay, so this will give the current and this will give the maximum limit of particular resource. Similarly, you can check for this core file, how much is the maximum size of core file. Okay, you can request, and what is the current size of core file that is allocated. So this is about get r limit and set r limit, which is used for getting the information about the resources allocated. The resources can be different types of files, or it can be a stack or a memory, okay, or it can be a virtual memory. Okay. So there are three rules. So three rules that governs the changing of the resource limit. If you want to change the resource limit, okay, you have to follow three rules. Okay. So the first one is, this is soft limit can be changed by any process to the value less than or equal to the hard limit. Okay, so this value can be less than or equal to the hard limit. That is the maximum value. Okay, so it should be less than the maximum value. Okay, suppose if the maximum value of a particular file is 500 bytes, okay, then the soft limit, that is the current limit, should be always less than the maximum limit. Okay, then any process can lower its hard limits to the value greater than or equal to its soft limit. So this maximum value, okay, that is the hard limit value, can be equal to the, or it can be value greater than or equal to the soft limit. Okay, so the hard limit can be greater than or equal to the soft limit. Okay. So the first one is, soft limit should be less than or equal to the hard limit. So you can remember easily using this. Okay. So soft limit should be less than or equal to hard limit. Hard limit should be greater than, can be greater than or equal to soft limit, and only the super user process can raise the hard limit. If at all you want to change this hard limit, that is the maximum allocated value for a particular resource, you need the root permission or the super user permission. Okay, so these are the three rules you have to remember when you are changing the limit of the resource. It can be either a soft limit or the hard limit. So moving on to the next one. So the next one is Linux kernel support for process. Okay. So you all know about what is a process. It's a program under execution. So whenever you create a program, the process will be created. Okay. So in Unix kernel data structure that supports process creation and execution. So in Unix, okay, important concept is it will support the creation of the process and the execution of the process. Okay, so you have already studied about in operating system what is the process, okay, how to manage the process. Okay. So a data structure and execution of the process are dependent on the operating system implementation. Okay. So for example, Unix has their own way of creating the process. Okay. They have own way of structuring the process and the execution of the process. Similarly, the Windows, if you come across Windows, they have their own way of creating and executing the process. So they are solely dependent on the operating system on which you run the program. Okay. So in the following, okay, you can see, so Unix process consists minimal of three things. Okay. So in Unix, there are three types of segments. So one is text segment, data segment, and tag segment. Okay. So there are three segments in a particular process. Okay. Whenever I create a process, a address space will be allocated for the process, and they will be having minimal three things. So that is text segment, data segment, and tag segment. Okay. So you can see here, so text segment, okay, they will be having machine executable instruction, your machine code, which will be in terms of zeros and ones, that will be in text segment. Okay. And the data segment, they will be having the global variables or static variables and corresponding data. Okay, we'll be allocating A is equal to 10. So that all will be stored in data segment. And similarly, you have stack segment. So stack segment will be having, uh, it will be having runtime stack, okay, which is called as runtime stack. So they will provide storage for function arguments. Okay, they will be having function arguments, automatic variables, written address. Okay, so this is very important. Okay, you have studied in this C programming. So stack is a data structure where we will be having the written address of all the active functions. Whenever you make a call to the function, okay, the written address, that is the next one. Okay, written address of this function will be stored in the stack. Okay. So they also will have function arguments. Okay, whatever the function arguments are there, even that will be stored in the stack. So these are the three things we'll be having in a process. So this is a diagram. So in the diagram you can see, so this is a process table, okay, which will be having several processes. Okay. And the process can also have a preprocessor region table, okay, which in turn will be pointing to a kernel region table, and the kernel region table will be having three segments, text, data, and stack segment. And again, the process will be pointing to a file descriptor table. Okay, so and even they will be pointing to the current directory root. Okay, so Unix kernel has a process table, as you can see, a process table in the diagram that keeps track of all the active process. So here you'll be having all the active process. So some of the process that also belong to the kernel. So there will be kernel will be also having some built-in process that will be stored here. Okay. So that kernel process, they are called as the system processes. Okay. So majority of the processes are associated with the user who is logged in. Okay. So whenever the user executes any program, he will be a process will be created. So they are all user process. So each entry in the process table, so there will be multiple entries. Okay. So each entry, so here will be pointing to a single entry. So this is a single entry. So entry in the process table contains, okay, the pointer to the, so you can see indirectly the entry will be pointing to data, stack, and text segment. Okay. And U address, U area of the process. So that is uh, the area, that is U area, is an extension of the process data entry. So here, so that's here U area is nothing but there is one more area which we call it as U area. So that is the extension of the process data table entry and contains other process specific data. So that is what it will be having So this is a U area. Okay. So along with process table, there will be a U area. So they will be having, okay, file descriptor. Okay, so file descriptor table will be there. Current root and working directory inode numbers and set of system imposed process resource limits. Okay. So U area will be having file descriptor tables, current root directories, inode numbers, okay, resource limits. So all those things will be there in the U area. So all the processes in the Unix system except the first process, okay, which is created by the system boot code. So the first program process will be created by the system booting. During booting time, the first process will be created, okay, which is created using, okay, you might be knowing about this system call. So that is fork system call. Okay, with the name. Okay, so this is the system call which is used for creating the process, okay, which we'll be studying in detail in the next chapter. So you can see here this diagram, okay, which will be the elaborated diagram. Okay, so this is a U area. So you can see here there are different types of process, parent child process, okay, different areas, and the process will be assigned with attributes. Okay. Apart from segments, it will be having attributes which are inherited from the parent or it can be set by the kernel. So every process will be having, okay, these many things. So first one, real user identification number, which is denoted by RUID. Okay, that is a user ID of the user who created the parent process. Okay, suppose if we are running a program, at that point of time, a process will be created, and that process will be having an ID, which we call it as a R, that is a real user identification number. Okay, and similarly, in Unix, we have not only just owner, we also have a group. Okay, so that group identification number, okay, the group ID of a user who created the parent process, which is called as group identification number. There one more, that is effective user identification number, okay, which allows the process to access and create files with the same privilege as the program file owner. Okay. So along with that, we have different other identification number. Just you can go through this. Okay. So here, okay, you can execute the program and you can access all this. You can display this numbers. Okay, process identification numbers and all you can display. So there are few more points you must know. So that is current directory. This is a reference or the inode number to the working directory. Root directory. This is a reference to the root directory. Then signal mask that specify which signals to be blocked. Okay, so these are all information will be there in a particular process. So controlling terminal, that is the controlling terminal of the process. Okay. Then process scheduling priority value. So what type of priority a particular process is having, whether it's given more priority, the priority. Okay, so that information will be there in a process. Okay, then signal blocking information, okay, access rights, okay, what type of rights it is having, process is having, okay, what is the root directory, what is the inode number. So all these informations will be there in the particular process. Okay. So along with that, you'll be having few more points, that is process identification number. If a process is created, okay, by a parent, then the parent, so you can have parent process, child process and all. Okay, so if a parent created a process, then what is the parent process identification number? Then pending signals, okay, signals, set of signals that are pending delivered to the parent process. Then alarm clock time, file locks, okay. So locking file locks like write lock, read lock, exclusive locks. So set of locks owned by the parent process which is not inherited by the child process. Okay, what type of lock a particular process is having. whether he's having write lock, read lock, and all. So that also information will be there in the process. Okay. So there are two important things. Okay. System calls, EXE, which you will be studying in detail in the next chapter. They are the commonly used together, okay, along with the subprogram to execute a different program. So using this system call, that is fork, you can create multiple processes, okay, to execute multiple programs concurrently. So you can create several processes, okay, using this system call. Then each child process executes its own virtual address space. That is, the parent process is not executed by the execution status of its child process. So these are the things. So this completes the second chapter of your third module. Moving on to the next chapter. So in the next chapter, you will be studying about process, introduction about process identifiers, fork, system call. What do you mean by V fork? What is the difference between fork and V fork? What is exit? What are different wait functions? Race condition. What is race condition? And exe function. So first one. So in Unix operating system, okay, there is an important concept that is called as a process control, which allows us, okay, which is used for executing the programs, and you can also go for termination of the process. So process identifiers, okay, so similar to your USN number, okay, every process will be having a unique process ID. Okay, so this process ID, it is a non-negative integer. So you have to remember, okay, it is a non-negative integer. Okay, and every process will be having a unique ID. Here, there are certain types of special process, and that process will be having special ID. Okay, for example, process ID 0. So process ID 0, it is used for scheduler process. Okay, they are all built-in process, scheduler process, which are used for scheduling or swappers. Okay, during the scheduling, job schedulings. Okay. Then you have process ID 1. So this is also important. The process ID 1 is allotted to init process. Okay. So init process which cannot be terminated. You cannot alter or you cannot modify this process. Okay, 0 or 1 or 2. So init process is a process which never dies. It's a normal user process runs with a super user privilege. Okay. The init process, and it's involved by the kernel at the end of the bootstrap procedure. Okay, during the booting of the system, these processes are used. Then we have process ID 2. Okay, so process ID 2, they are also called as page daemons. Okay, so this process with ID2 is responsible for supporting the paging concepts which you have studied in virtual memory. Okay, so you have studied in operating system paging concepts. Okay, in virtual memory. So that time this daemon process is used, which is having the built-in ID2. Okay, so paging of virtual memory system. So this process is also called as kernel process. Okay, the other name for daemon is kernel process. Okay, and here there are a few functions. Okay, so following are the functions, and you can see their written identifiers. So you can see you need this header file. Okay, to if you want to use this function, you have to go for this header file. And here we have function get PID. So that get PID is used for getting the process ID. Then get PPID, it is used for getting, okay, the parent process ID. Okay, so there can be, you can have parent process. So you can have the parent process. This parent process can also create number of child process. Okay. So at that time, if you want this parent process ID, then you have to use this get PPID. Then, as I already said, a process will be having a unique identification number, that is real user ID. Okay, the effective user ID can be, you can get using this function. Okay, so this is used for getting the group ID. This is for getting effective group ID for the calling process. Okay, so these are different identification numbers will be there for the particular process. So I'll just execute this program. So this program, you can see here, I am creating a process. So this is a function, okay, which is used for creating. Fork is a function which is used for creating a process. Okay, so a process when it is created, it will be having returned with ID. Okay, it will be, if it is capable of creating, it will return 0. Okay, so if it is 0, so it means that you have successfully created the process. Okay, then you can get different IDs. Okay, you can see here get PID and get PPID. Okay, you can see to this program, okay, it will be displaying. Oh, there's interesting. So meantime, we'll continue with the next one. I'll just show you later, okay, what this function program will give the output. The next one is we are studying in detail about fork function. Okay. You can see here. Okay, so get PID and get PPID. So this is a process ID and this is a process parent ID. Okay, so you can see this is different ID. So like this, you can try this different functions. Okay, this all these functions you can try, okay, to get a different ID. Okay. So the next one is fork function. So fork function, it is the only way you can create a new process. Okay. In Unix kernel, is when an existing process calls a fork function. Okay, so this is a system call which is used for creating the process. So these processes are created specially by the kernel. Okay, so then you can see this is a prototype. So you need these two header files. Okay, and this is a function, and with the parameter, there is no parameter, it is a simple fork. Okay. Void means there is no prototype, this one parameters. And here when you call a fork system call, okay, it is used for creating a process. Okay. Assume that we have a process. Okay, it's a parent process. I'll just give a name as P, and you execute a fork system call. Okay, this fork system call will be executed, and here a new process will be created, okay, which we call a child process. Okay, a child process will be created. Okay. So this function is called once but returns twice. When you call this function, okay, there will be two return types. Okay. Usually, when you call a function, there will be only one return value, but here there will be two return values. Okay. The only difference in the return is that the return value in the child is 0. That means there are two processes here, parent process and the child process. For the child process, this function will return 0. Okay. And while the return value for the parent is the process ID, okay, of the uh, child process. Okay. So assume that this is having some process ID 123, and this newly created process will be having some ID, okay, 124. Now, when you invoke this fork system call, a new child process will be created, and it will be returning two values. One is 0 for the child process, and for the parent process it will be returning the ID, okay, the ID of the child process, that is 124. So there will be two return values, one is a 0, another one is 124, that is the ID of the new created, okay, the process ID of the new child. Okay, so this is just an example, okay, with the different ID 123 and 124. So let's understand with this example. So here we have a simple program. Okay. Now here we are using a fork system call. Okay. There will be when you execute this program, okay, a process will be created. Okay. So this is a process for your program. Okay, the main process. And you can see there are two functions. One is fork function and printf function. Apart from that, they will be having some uh, data, that is variables and all. I'm not writing all those things, but I'll just write the function name. So there are two functions in this process. Okay. So this is a process for your program. Okay. When you execute this program, a process will be created. Okay. Now, when program starts executing, when you encounter this statement fork, a process will be created, a child process will be created. Okay. This is your child process will be created. Okay. When you execute this fork system call, okay. Now this is child process, okay, will be having a different address space. Remember, okay, this will be having different address space, and even this will also will be having a different address space. Okay. Both the child and the parent continue executing with the instruction that follows the call to the fork. Okay, the child is a copy of the parent. This is very important. The child is the copy of the parent. Okay, you can see this is your printf statement. That is this one. Okay. Now both the child gets a copy of the parent data space. Okay, whatever the data that is there in the parent, when the child will get, they also will get the space in the heap and even in the stack. Okay. The parent and the child do not share these portion of the memory. That means they do not have the same address space, but they will be having, okay, they are the copy, but they will be having all the data which is there in the parent will also be there in the child. Okay. Now, you are executing this fork, a child process will be created and they will be copy of the parent. So they also will be having all those things, functions, data types and all. Now, okay. Now, when parent and child starts executing together, okay. Now you have not just one process, two process. Now both the child and the parent continues executing with the instruction that follows the fork. What is the next instruction? That is this printf statement. Okay. Now even the child will also will start continuing this next instruction. Okay. So there will not be only one execution. There will be two executions. Okay. So this is one of the beautiful concepts that you have in fork. Okay. Both the child and the parent continue executing the instruction that follows the fork. So what will be the output? So it will be having the output process created twice. It will be printing process created twice because it will be executing these once the parent process will execute, next the child process will execute this statement. Okay, so we will be having the output process created twice. Okay. You can see here, I just copy this program. Here, process created. It will be printing. Okay, you can see here twice it will be printing process created and again it will be creating process created. So two times it will print the uh, printf statement. One will be printed by the parent process and the next one will be printed by the child process. Okay. So this is one more program So here we have some external variables. So this is one variable. So there is one buffer which is having some statement. Okay, and here there is one more variable with the value 88, which is a local variable. Here you are calling the write function, that is write API. Okay, so you know the syntax of write system call. So program that is file name. Okay, then a buffer, okay, which contains data that you want to write. So this is the data that you want to write, and the size of the buffer. Okay, so you are checking if it is not equal to the size of buffer. Okay, so if you are not able to write, then you are printing some error message. Okay, so suppose if you are able to write, okay, then it will print this. Okay, whatever you are printing, okay, that will printed in the screen. So this will be printed. Okay, the statement will be printed. Then before fork, okay, so here if PID is equal to fork, so that is you are calling the fork. Okay, so this is your main program of your program process, main process of your program. Okay, you can call it as a parent process. I just give it as P process. Okay. So this parent process will execute this fork, okay, and a child process will be created. The child process, okay, if it is able to create successfully a child process, it will return the value 0. Okay. Now now assume that you are able to create the process, child process. Now you check the condition, 0 is less than 0. Okay, condition fails. So it will go to the it will check this one. Okay, whether PID is equal to 0. Yes, the PID is equal to 0. Okay. So if it is 0, so assume that this is having the ID something like 430, okay, and this is having the ID 429. This is, yeah, this is 430. 420, 430, and let us assume that this is 429. So here it is having fork system call. Okay. And here there are some variables, okay, like global parent will be having variable global, where and all with the value 6 and 88. Okay, and here child process will be written with the value 0. Now you are incrementing the value of global, okay, which will become global, which is initially 6. Now it will become 7. Okay, that value will become 7, and VAR value will become, it is 88. Now it will become 88 plus plus, okay, it will become 89. Okay. And you have a printf statement. Okay. Similarly, the child process will be having the copy of this, okay, one fork and one printf statement. Okay, both will be having different address space. Okay, that is important. Both will be having different address space. Okay. not the same. It is not pointing to the same address space. It is a copy of the process. Okay. Now this printf statement. Okay. When you execute this fork, a child will be created. Okay. Now you have incremented the value of global and you have incremented the value of where plus plus. Okay. Now you'll be executing the printf statement. Okay. First, always the child printf statement will be executed. Okay, the child printf statement will be executed. What is the child value? It is 430. Okay. What is the PID? It is 430. Then what is the value of global? So for this child, when you created the child, you have incremented the value of global and where. Okay, what is the value of global? It is initially 6. Now 6 plus plus it will become 7, and where value will become plus plus it will become 89. Okay, so this is about your child process. Now coming to the parent process. Okay, so it is okay. So this is the value of child process. Okay, I have written here. So now coming to the printf statement of the parent process. So parent process when it executes, okay. So this is only when you are creating the child process. That is only when PID is equal to 0. So PID will be written 0 only when you create the child process. So when you create the child process, you are incrementing the value of global and where. But when you are creating the main process, this incrementation will not come. So your parent will be having the ID that is 429. Okay, parent ID is 429 and global value is initial value. What is there here? It is 6. Okay, then where what is the initial value? It is 88. Okay, so this is about your child process. Okay, and this is of your parent process. Okay. So here this you have to understand only when PID is equal to 0, that is PID is equal to 0 only when you are executing the child process. So this is the child process. Okay, only for the child process. So the next one is the file sharing. So file sharing will continue in the next session. To answer attendance, Naresh,
Present, ma'am.
Navina,
Yes, ma'am.